So one of the key applications of the derivative is the ability to easily find the maxima and minima of a function. So maxima and minima are the plural forms of maximum and minimum. So this might be kind of a new concept, right? You might think of maximum and minimum as being one singular thing, right? So why would it have a plural form? Because generally, if you talk about something having a maximum, there's only one of those, right? It's the maximum. It's the largest thing. And same with the minimum. So this is where we'll get into the difference between absolute and local maximums and minimum. So first, let's define a absolute maximum, and I'm just going to do the definition for maximum because I think it's pretty clear how to change it to minimum. Hopefully, so let's just write down the definition just for what an absolute maximum is. Okay, so here we're going to say let f be a function defined over an interval. Okay, say I. Maybe we'd say a to b or something like that. But if we don't need to give the endpoints names, we'll just call it interval I, and let c be in I. Then we say f has an absolute maximum on I, on this interval, if, keep missing words, sorry, on I at C, if f of C is greater than or equal to f of x for all x in I. Okay, so there's an absolute maximum on this interval at C if it is larger than every other point on that interval, right? So hopefully this makes sense intuitively. And of course, if you wanted to find an absolute minimum, you just flip around the sign, right? It would be an absolute minimum on I at C if f of C is less than or equal to f of x for all x in I. So some examples that are easy to see graphically. Okay, so if we just look at f of x equals x squared, and we look at maybe we just look at the interval -1 to 1, or really we don't even need to do that. We can, one of the reasons we didn't define it as a to b is that it doesn't need to be a finite interval, right? We could look at -infinity to infinity, and we can see that on this interval, there's an absolute minimum at the vertex, right? Which in this case would be 0, 0. So there's an absolute minimum at, because we're calling it C, we'd say at x equals C, which in this case would be 0, right? So this is because f of 0 is less than or equal to f of x for all x in -infinity to infinity, right? And this is really just about knowing the range of x squared, right? That range of x squared goes from 0 included to infinity, so 0 is the lowest point in this case. So in general, naturally, a function can only have one absolute maximum or minimum unless there's a tie, right? So if there's a tie at certain points, like if there's a function that looks something like this, maybe, right, where these are at the same level, something like that, then maybe there's a tie for the absolute minimum. But in general, they're there's only one f value where there would be the absolute minimum or maximum, when you might have several x values at that same point. So sine of x, for example, right, which oscillates between -1 and 1, going in both directions. This one has several absolute maximum and minimums on -infinity to infinity, namely at every, not every multiple, but every pi over 2, and then at every pi over 2 plus pi k, right? Where k is any integer. So, or rather 2 pi k, I should say. So you can have multiple of them, but they would all be at the same f value, right? These would all be at 1. So then the next question we might ask is, okay, there's only one possible absolute max or min, or a tie for that max or min, but do we have to have one, right? So that would be the next question. And if we're considering an entire infinite interval, then no, we don't necessarily need to have one, right? We could just look at an example. Probably the simplest possible example of a function is the function y equals x, right? Or f of x equals x. So just a straight line with slope 1 and y-intercept 0. If we're looking at -infinity to infinity, there's no absolute max or min, right? So the next question then would be, okay, well, when do we have an absolute max or an absolute min? Okay. So this is the theorem known as the extreme value theorem, which tells us when we have an absolute max or min. So the extreme value theorem. Okay. So this says that if f is a continuous function over the closed bounded interval AB. Okay, so it's closed, meaning the endpoints are included, and it's bounding, meaning that they're finite. Then there is a point in AB at which f has an absolute maximum over AB. And then the same thing for minimum. And there is a point in AB at which f has an absolute minimum over AB. Okay, so of course we don't have to have these conditions, but this is telling us that if we do have these conditions, if we have a continuous function and we're looking at a closed bounded interval, then we are guaranteed both a absolute maximum and an absolute minimum. Okay. So going back to the y or f of x equals x example, what if we just look at the interval from -2 to 2? So this is a continuous function. Before we were looking at the entire function from negative infinity to infinity. So what if we cut it off here and we only look at from -2, x equals -2 to x equals 2. So the function is going to look something like this. Now we do have an absolute maximum. Okay. And we do have an absolute min, right? And it's going to be the endpoints in this case. So in general, and this is going to be kind of the strategy related to the strategy for finding an absolute max or min, is we're always going to need to check the endpoints, because if we have a strictly increasing or strictly decreasing function, then your endpoints will be either your absolute max or your absolute min. But there's going to be other points we want to check in the middle as well, which we'll talk about when we get into the discussion of critical points. But they're basically going to be where the derivative is 0 or where it doesn't exist. Okay, and that we'll talk about that in a future video. So if we have something that looks maybe like actually let me make it something more like this. Okay, so I'm not going to give a name to this function. Let's say that this is like 6 and this is like -7, for example. So we're looking at this function f on the interval from -7 to 6. Okay, so we can tell from the graph that it is continuous, and it is a closed interval. The endpoints are included, and it is bounded, right? It's all finite. So we can see that there is an absolute max and an absolute min here, and we can just kind of tell what it is from the graph. Again, we're not actually labeling what these numbers are. It doesn't really matter here. We're just looking to locate them. So this would be the absolute min. In this case, though, for the max, the endpoint isn't necessarily the largest value, or the largest y value, right? So here, this would be the absolute max. Okay. Okay, so just a couple more examples. I want to be clear, like for something like cosine of x, we looked at sine of x, but just to look at the other trig function here. So if this is 1, right, and it looks like this, it's oscillating. You know, when I say that you can only have one absolute max or min, I'm specifically talking about the y values. We usually define the absolute max and min at the x value. So looking at it from the point of view of the x values, you can have an infinite number of absolute max and mins. They'll just all be at the same y value. So we wouldn't write that there's only one absolute max or min here. We would still write that the absolute max is at x equals 0 plus or minus 2 pi k. Again, where k is any integer. And then the absolute min is at x equals, this one's going to be pi over 2. Or sorry, not pi over 2, but pi. It's undefined, or not undefined, but 0 at pi over 2. So again, plus or minus 2 pi k. Okay, so we can have an infinite number of them. They're just all going to be tied at that same y value. And this is, of course, looking at it over negative infinity to infinity, the whole domain. Another situation we could have, if we look at f of x equals x over 2 minus x on 0 to 2. So 0 is included, 2 is not included. Namely, 2 is not even included in the domain of this function anyway. So here the extreme value theorem does not apply because it's not a closed interval, first of all. And even if it was, it's not bounded because it's going to be going off to infinity at 2. So, or rather the boundedness actually refers to the x value, not the y value. So it would be bound. This is a bounded interval. So let me just be clear. This is bounded, but it is not closed. Okay. Because, again, the 2 is not included. So it's not closed. So the extreme value theorem does not apply here. So this means that we're not guaranteed an absolute max or an absolute min. But do we have either of them? So if we just look at the graph here, rather than drawing it, we can look at the nice version. So we're just looking between 0, which is 0, 0 in this case, and 2. So we can see how it's going off towards infinity at 2, right? So we're not going to have an absolute maximum because it's going off to infinity. It's not going to be able to be cut off anywhere, right? And at 2, it's undefined, and then it comes back around over here. But we will have an absolute minimum because 0 is included, right? So it goes down to 0, 0. Every other point is above 0, 0. So in this case, because 0 is included in that endpoint, we would have an absolute minimum, an absolute min at x equals 0. Okay. So, and sometimes we might say that the minimum is at, we would say the minimum is at 0, and that the minimum is, in this case, also 0. But just a little bit about the language that you might see here. The absolute minimum at x equals 0, and the absolute minimum is 0, which refers to the y value, right? So let's say y equals 0.